G'day guys, welcome back. In this particular video I'm going to be showing you how to draw the shear force diagram and bending moment diagram for the beam below. So what we've got here is this 6 meter long beam. It's simply supported, and what we've got here, interestingly enough, is this linearly increasing distributed load. And at this particular point just here, we're given that the distributed load is 30 newtons per meter, right? And just so there's no ambiguity about how I'm going to solve this problem, I'm going to be solving this using these formulas. dv dx is equal to minus w, and dm dx is equal to v. So rather than solve this using first principles, like I've shown you how to do for our previous videos, I'm going to be solving it using these shortcut formulas. Okay, so the first thing you want to do when it comes to these types of problems is draw a free body diagram. I'm not going to focus too much on the aesthetics of it, but that's our beam just here. And of course, because this is a pin support, we're going to have AY just here, and we're going to have AX just here. And because this is a roller support, we're going to have BY just here. Now, rather than draw the distributed load like I've got just here, which would be totally appropriate, I'm going to instead replace this distributed load with an equivalent point force, right? So I'm going to try and replace this distributed load with an equivalent point force somewhere along the bar, okay? Now, we know from a previous video that I've made that the equivalent point force due to a distributed load is actually just the area under the curve, right? And of course, we can evaluate this using the integral, but because this is just a line, this boils down to finding the area under the area of a triangle, which is a half times by the base times by the height, which is that, right? And of course, you can tell this is going to be a half times by 6 times by 30, which is 3 times by 30, which is 90. So basically, the net force due to this distributed load is 90 newtons, okay? But where is this point force located? Well, I've also shown in a previous video that the centroid of a triangle is located 2/3 along its base. So that means that this is going to be 2/3 of the total length of this bar, which is going to be 4 meters. 4 meters just here. That is our free body diagram right here, okay? Now, what I'm going to do is I'm going to power through this, and I'm going to show that the sum of forces in the x direction must be equal to 0. That means straight off the bat that AX is equal to 0. So far, so good. Let's get rid of this little guy. Now, let's do the sum of forces in the y direction is equal to 0. That means we know that AY plus BY minus 90 is equal to 0, but I'm just going to write that as equal to 90. Right? We can't do this yet. 2 variables, 1 equation. We need the sum of moments is equal to 0. So let's do that. The sum of moments about any point is equal to 0. I'm going to choose the sum of moments about point B this time. So let's do that. Well, what's the sum of moments about point B? Well, we've got 2 forces which produce moments. This one will produce a moment equal to 90 times by the perpendicular distance, which in this case is just 2 meters. Right? It's just 2 meters, right? And that's going to be equal to the moment produced by this force, which is going to be the magnitude of the force times by the perpendicular distance, which is just 6 meters, okay? This turns into algebra now. This is 180 divided by 6. AY is going to be equal to 30 newtons, okay? I apologize if I'm powering through this. I just realized there's not much time and I've got to really get through this as fast as I can. All right, now BY is going to be equal to, let's see, you can find it from this one. It's going to be 90 minus 30, which is 60 newtons. Okay. So we found AY, we found BY, we're ready to start diving into the mathematics. So what we're going to do now is we're going to find the value of our shear force using this formula just here. So once you rearrange it, you're going to get V, our shear force, is going to be the integral of minus W dx, where W is simply your value of your distributed load at a point X, right? So to do that, to find the value of W, we need to find the equation of this line just here. Well, fortunately for us, x is always defined by convention to be from the very left point of from our beam. So this is just the equation of a line which passes through the origin. And that's quite easy. We actually know that. We know that this is going to be, W is going to be the equation of a line which is the gradient, rise divided by run, 30 divided by 6 times by x. This is the equation of our line, or if we like, the equation of our distributed load at a point x. Now, if you don't believe me, plug in x is equal to 6 meters and you'll get 30. So it's purely consistent, okay? So what we're going to do is we're going to plug this into here, and that's going to be equal to the integral of minus w, which is 5x. So it's minus 5x dx, okay? And when you evaluate that, that's going to be minus 5 times by x squared divided by 2 plus an integrational constant, which I'll call C1. Okay, so I realize I'm just powering through the integration right now, but I hope you can follow me. What we need to do now to solve for our shear force at any point x is to solve for our integrational constant. So we know that when x is equal to 0, v is going to be equal to, let's see, what is it? We need to find that. So what we're going to do is we're going to resort to our free body diagram to find out what our shear force is at a point 0. So to do that, I'm going to be making a cut section right along here. And I'm going to draw it here so you can see. This is going to be our cut section, just here. We've made a cut section. We know that this is going to be our shear force just here. It's going to be V. This is going to be our bending moment, M. And this is going to be our reaction force, AY, which we calculated earlier, which is 30. And of course, we're going to have the small snippet of our distributed load just here. This is going to be our small snippet of our distributed load. Now, to find our shear force at our point x is equal to 0, we're going to shrink this cut section closer and closer and closer to our point A, to the point that this distance is actually negligible. Right? So imagine you're making your cut section, it's like right along here. You're making the cut section right along here, right? Such that the force produced by this distributed load is 0 and the moment produced is also 0, right? Which means that V is going to be equal to AY in that particular case. V, which is your shear force at your point at your point A, is going to be AY. I hope that made sense, guys. What I've done is I've made a cut selection right at the point A to find for your shear force when x is equal to 0. Okay? And we solve for this now, and when we can plug in solve for C1, and we know that V, our equation of our shear force, is going to be equal to minus 5 on 2 x squared plus AY, which is going to be 30. Okay? That is the equation of our shear force just here. Okay, now we're ready for the more interesting part. Let's do the second formula just here. We know that our moment is going to be equal to the integral of v dx, Well, we know what v is as a function of x. We just found it. So let's plug that in here. We know this is going to be equal to the integral of minus 5 on 2 x squared plus 30 dx. This turns into pure integration. This will be minus 5 on 2 times 3, which is 6, x cubed plus 30x plus another integrational constant, which I'll call C2. Well, we know when x is equal to 0, we know that our moment at that point is also equal to 0. Refer back to this. Remember, if this cut section shrinks closer and closer to 0, your sum of moments, you can prove it, is just going to be equal to 0, right? So m is going to be equal to 0. Okay, so that means then C2 just turns into 0, which means that our m is going to be equal to minus 5 on 6 x cubed plus 30x and plus 0, which is our answer. There we go. We found our equation for our bending moment. And for our shear force, now all we need to do is plot the thing, right? Now, typically what we do is we draw the shear force directly under this so you can actually see the correlation, but I don't have enough space for that, so I'll try and plot it all here. This will be our shear force diagram just here, plotting V versus X. And this right here will be where I draw my bending moment diagram, like that, where I plot M versus X. Now I'm going to try and power through this graphing here because it doesn't really test your skills so much. It's more of a trivial activity. So let me just do this quite quickly. We know that V looks like it's the shape of a parabola, which has simply been shifted up 30 units. So let's draw this parabola just here, and it'll look something like that. This is our part of our parabola just here, and of course it's shifted up 30 units, so this is going to be 30, and you can solve for V when X is equal to 6 to find out what this must be, and of course it's going to be minus 60. Okay, so this is our shear force diagram. Now typically what we do is we shade it in to make it look pretty. I think it's a pretty useless thing to do, but we do it for some reason. Now let's do the bending moment diagram. And to help me draw the bending moment diagram, rather than try and plot this thing, which will be quite tough, what I'm going to do is realize that V, the equation of V, is actually the equation of the gradient of M, right? So I realize that first M starts at 0, just here at the origin, but it starts off with a positive gradient, which is going down. So it'll look like this. It'll be a sad looking curve like this, right? And then we notice at this point just here, and when X is equal to this point, it has a gradient of 0, so it's going to be a stationary point. And then it's going to just plummet downwards. The gradient will be negative and decreasing, so it'll look like that. That'll be closer to what our bending moment diagram looks like. And you can plug in X is equal to 6 to show that the value at this point is in fact 0. So it starts at M is equal to 0 and it ends at M is equal to 0, right? And solving for this would be quite challenging, and I'll let you do it in your own time, but this value is 69.3 Newton meters. This corresponds to our maximum bending moment, which is also corresponding to a point and when X is equal to this just here, because that's our stationary point. I apologize again for rushing through the drawing of the shear force diagram and bending moment diagram. It's really an exercise in mathematics, not in statics, so I didn't spend too much time on it, but that's how you approach these types of problems. I hope that made sense, guys. Cheers.